Okay, this is a separate project, and as I said yesterday, this has a long history in our group. Simon Shaw, Ji-Chung Wang, Hong Lu, among others, yes? This is the inverse scattering series says you can do everything without subsurface information. So how about depth? Okay. So this is, I want to get to a point here where you know what we're going to be delivering, okay? So a lot of this is not new for those who have seen our presentations, but we want to take you to a point where, yes. So, for those who haven't seen it, we need to show you this movie. This is Simon Shaw. This is a 1D application. In other words, Simon went inside the inverse scattering series and looked for terms and collected terms that deal with depth imaging. Only moving water speed migration with their incorrect amplitude to the right location. Not for yes? In other words, a water speed migration takes every event, yes? This assumes the multiples are out, yes? And takes it and places them where water speed would locate. So you're not going to get a reflection coefficient that way, yes? Because you're not using the actual velocity of the medium. So the objective here, again, we do, even though people are uncomfortable sometimes with what we do risk manage. If we said we were going to do an image at the correct depth with an amplitude on that image that's ready for amplitude analysis, that's a higher bar. The series says you can do it, but you're biting off more than you should at one time. Just get structure, yes, without velocity. So everything you see here, everything that we will deliver in this project is just going to be for structure. So this is a 1D example, and this is water speed, faster, faster, slower. This layer here is slower than water speed. And Simon generated data in this acoustic model, and this center line here is a slope water speed migration. What is it called? It's called Claerbout 3. We didn't call it that back then, just slope migration. Now we're in this Claerbout 1, 2, 3. It's Claerbout 3. Understood? Like that. That's what slope is. Slope migration is Claerbout 3. So then this is like a V1, some kind of image, linear image of water speed. And then this gets input into a subseries of terms that was called back then, and still called LOIS, Leading Order Imaging Series. A selection of terms, yes? And that algorithm, which Bob Keyes, who's then at ExxonMobil, now at ConocoPhillips, made into a closed form. So it's rocket fast, yes? So when we stay with homogeneous, we have closed form. In other words, all of what you see are closed form, which makes it a tremendous advantage. There's not round off errors, yes? It's like A over 1 minus R. So all these higher and higher order algorithms are closed form. If we did a variable background, we would lose that because it's numerical. The G0s, even if we made a variable background and went through with a WKBJ, it's not exact already. It's a high frequency. So to date, we have stayed with homogeneous, yes, for that reason. We just get more capture in closed terms. You can see a sequence of that happening. So I'm sure. So in this There's an error. So this is Simon's famous movie. And that's telling you the number of terms in that leading order imaging series that are being added. At that time, back then, we did not have a closed form. And I like that. Now, with a closed form, you just get the result. With those, back then, we added 2 terms, 3 terms, 4 terms. You saw the action, you know. When Simon first did this, we were going to shut down the project because the screen went green. The whole screen went green. I mean, it went, you know, bad news. We were ready to say, let's go back to multiples. You understand? But what was going on, this was very agitated, but the algorithm, yes, and but he took more terms and they calmed down. One of the interesting things you'll notice is the number of terms that it needs. The number of terms that it needs is determined by the data. In other words, this is located correctly, mislocated, mislocated more, mislocated yet more, mislocated yes, less. This is less mislocated than that. Why? Because of this. Understand? So the overall error in velocity is less to this than it is to that. So this has a bigger error in depth than that does. Clear? The deeper one is less in error. So when you watch this, do this story, all this kind of group therapy, this thing talking to itself, this guy gets happy first and stops. And this guy's still needing more therapy sessions with this talking to itself. What happens in this algorithm is they determine who's mislocated and they talk to those above them to give them help towards that goal. I mean, that's what's going on in these diagrams. So if you watch the movie again, so it's not any way kind of stripping, understand? Well, I'll make you happy and then I'll make you happy. And, you know, it's not that. They talk amongst themselves 2 at a time, 3 at a time, and this decides by itself when it's happy, well adjusted, ready to move out. No more psychotherapy here. Yes? Watch. We should do these terms again. See, the bottom got happy. This guy stopped talking, and this guy still needed more help, more conversations. And when they stop needing, they just stop talking. Yes? We don't tell it to stop. That's interesting, right? This was just calculated away. Understood? Yes. Now, when people first saw it, they said, oh, look at the small contrast. Yes? These are small contrasts. Yes? Of course, people will say that. And that's why it's called leading order. It has some capture, not all capture. Yes? Along comes Professor Fang. Well, first, this is the pre-stack version. This is Simon's work still. This is, it's not. Let me get that arrow up. Yes. The movie doesn't want to go. Again, it comes to a common image gather flat, and it just stops. And so that's a pre-stack version of what was there before. There's no distortion, yes? Just, okay, that's Simon Shaw. So along comes Professor and here's a salt model, big contrast, 1546. Notice all these things, all these models that you're going to see to some point are only velocity. Why? I figured in the world of trying to find structure, the only thing that matters is knowing the velocity. If I only want location, density doesn't matter. Density will change amplitude, but it's not going to, if I have the velocity, then I will locate, yes? Density will affect amplitude analysis, yes? So I figured just do inverse scattering in models that don't know the velocity. Because if I knew the velocity, I could find the depth. So assume that all we need to do is use models that don't know the velocity, yes? Okay, that whole thought is wrong. But that was my thought, okay? Understand? Okay. It doesn't, it's not quite, but that's what drove all these examples. Well, this is, you'll see examples here with Fang, which is called higher order, more terms. Yes, higher order terms. Higher, but not all terms. Very far from all terms. Okay. This is a water speed migration that you've seen before, for the water bottom. The red are the actual reflectors. So you have 1, 2, 3, 4, 5 reflectors. Your images are 1, 2, 3, 4, 5. This belongs here, is up here, with water speed. Yes? A little far away. Yes? This guy is up, hanging in through here. That's a water speed migration. This water speed migration goes into Professor Fang's closed form algorithm and produces this. Yes? The speed of the most expensive part of Professor Fang's algorithm is the water speed image. That's a Stolz single water speed migration, which is lightning fast, right? 30% time after that, that closed form gives you this. But you got to do that water speed very well. So if people want to know how to do Fourier migration very well, I would talk to Professor Fang, because you got to do the wrong thing right. In other words, it wants the linear term to be the linear term. There's no fixing it, yes? The quadratic is doing its own thing, yes? So now you have Zicheng Wang with higher order imaging series plus leading, plus laterally exclusive terms. Terms that only occur in the series if you have lateral variation. How does it figure that out? Because it looks at the water speed image and it looks, is there any X variation or Y variation in the image? There are terms that look like partial respect to X of the water speed image. You understood? There are terms in Professor Fang's, it has no terms like that. Yes? So this, you can see the walls of the salt. Also, this is closed form. Yes? So we see this, we said we're going to field data. Okay? Wrong. Okay? So I went, where was I? I was at a sponsor BGP Bulletin, and Mike Richardson will show this. He's a former Shell, yes, capable guy. Walking to the garage, he says, you know, most of those reflections in the world, they have density. I said, well, of course I know that. That was, you understand this? We're dealing with, this thing is having all these communications with reflections. Just what you want to avoid. By smoothing, it wants sharp and reflections. But this theory assumes that all the reflections are called by velocity change. Because you made it like that, yes? So every time it sees a reflection, it assumes a velocity change. It won't better talk to you, you know? That kind of thing. So, well, let me just show you full shadow. It's another popular problem. This is water speed. This is Fang Lu. This is Zicheng. Closer, all of this capture, everything we've done, even within velocity only, is very partial. Understood? It's a set of LOIS, HOIS, HOIS plus LE. It's the tip of the iceberg of terms, even in that velocity only model. Clear? Yes. But that's okay. I mean, we're seeing, so once we got that that thought, the first thing we did is we tested Professor Fang Lu's imaging, make a model where the velocity and density varied. Yes? but do your processing as though it's all velocity, and the results are horrible. Because you make a density change only, it thinks it's velocity. It starts talking. A density change doesn't belong in the conversation, yes? For example, if you have C0, 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 yes, well, everywhere but density change, you don't have an imaging problem. It's just C0, right? Just migrate with C0. But if you give it an algorithm that says every reflection is velocity change, they'll start talking for structure, and there's nothing for them to do. So the thing that we did was, don't do your inverse scattering series with velocity only. Make it acoustic. Velocity and density, make it elastic, and we have Haiyan, the champion of bringing that to elastic. Yes, we have Hong who followed, Shuli, people. We had a whole group of students taking this to a world where it's what we needed, yes? So, before I go there and show you the amazing what that work does, is we plan to have two kinds of delivery. If there are places in the world where it's the main generators are velocity, then you're going to get this. Yes, it's free. A single water speed migration, one velocity, plus 30% in time. Yes, it doesn't have to be everything to get that picture. You know? That's a valuable picture to get the water speed. So, and when there are density variations of significance in those regions, we will provide this next kind of capability that I'm about to show you, yes? Where it has, in other words, the interesting thing is, if you make the theory only velocity, it doesn't have the ability to distinguish. You told it it's velocity. So every reflection is in the conversation. As soon as you say, let it be velocity and density, and you say, now look at the imaging terms, you will see in the integrand, it's figuring out, is that a density change? Yes? And if that's a density change, it won't include that reflection. That's amazing. You understand? That's because of directness. You understand? Once you put in, so for example, another thing that we learned from Haiyan, when you have one parameter like velocity only, then every reflection means somebody changed in that world, right? You got a one parameter world, a reflection means velocity changed. When you have two parameters, velocity and density, if you do a linear inversion for velocity and density, you can get a prediction of a change in density, and there is none. You understand? Leakage, they call that in AVO, because you have a nonlinear relationship, and I just inverted linearly. Yes, you get problems. Well, when you do the multi-parameter version of this, you get terms that are doing AVO, and you get a term that's dealing with leakage. Amazing, you understand? As soon as you get more parameters, it knows, I don't know how it knows, but it knows there are issues that don't exist in one parameter, and terms arise. That's what I'm saying. When I'm impressed with the series, is because as soon as you formulate it, it knows it has things to do. If you said to me, you go write a term down that's going to deal with leakage, I wouldn't know where to start. You get the point? Well, it's the brain that's in that series you saw that is so amazing to us. We're just mining it. This is Marmousi. Again, Marmousi for velocity only, yes? But what is important is here is, you see there are terms here. See this term? This is a lateral. Alpha 1 is a water speed slope migration. This is looking, this kind of term is not being included now. That's a lateral term. in Fang's work, yes, it's just terms which have, in other words, an imaging issue in multi-D, but also exists in 1D, yes? I'm just trying to let you know that. So here's Marmousi. Here's the shot again. Here's the pre-stack water speed migration, where you're seeing the difference between where it needs to be, and we'll flip back and forth, and where the water speed gives you. You see that? Yes. So the places where you have not much lateral variation, no lateral variation, it's doing very well. As soon as you move to this region, it does poorly. There's lots of lateral variation, yes? But it makes nothing worse. Understood? And it's closed form. In other words, let's flip back and forth. There's some benefit, but not. So how do we know benefit? How do we know for something like this or field data? Let's say the world was actually only velocity. How do we know when this algorithm is happy? When it's doing what it needs to, and when it needs to do more? There's the business of common image gather flatness, which we use normally as a replacement when we don't know how to find the velocity. We look for that quality. That's a necessary but not sufficient condition, that you have the right image. Here, when the common image, in other words, when you take a view of that image point with different subsets of the data, when the common image gather is flat here, it means a direct method is happy. It means, like Simon's movie, stop talking. So you'll see in this in a minute, places over here where it's flat, and over here where it's curved. Means you haven't given it enough. Understand? It gives you a signal from different places. You have not given it enough terms. In particular, lateral bearing terms. Let me just show you those pictures. In other words, here you're getting these different subsets of the data. And you're seeing, now you're going to see A, B, and C with what happens at different subsets of the data, what we would call common image gathering. So there are places here where it's a relatively flat. Yes, this is water speed and it's not flat. You know it's not happy. Then it gets flat, it's over on that left side. The left side where the structure was flat. You get to that middle part, it's not as happy. Well, here's water, but you get here and it starts to be less satisfied. This is with ISS imaging, yes? So you have an indicator of when a direct method is working and not working, yes? But let's get to this density business. Okay, this, as it says, Fang and Hong both are here. Julie is at CGG at the moment. Yes. Hyan's here, Hong is here. So this is taking what you saw before, first into acoustic, multi-parameter, yes, then elastic. And so this is the normal AVO. In other words, G0, V1, G0, acoustic-wise, where you get your usual angle dependence, yes? Between two parameters, here and here. This is an interesting case. You got data equals G0, V1, G0. The next guy is G0, V2. G0 is minus G0, V1, G0, V1, G0. Same guy here as here. how you invert to get alpha 1, beta 1 is exactly how you invert to get alpha 2, beta 2. Yes, that's what that says. Remember we said it's the same G0 all the way down the line. Okay? What's going on here, on the right-hand side, there are terms. This is the first nonlinear term. This is the first term beyond the linear, meaning this, in the acoustic case. And you have terms like this, yes? And you have, these terms don't have integrals. In a one-parameter world, you'll get a term like this. And you'll see in a second when we do this comparison of iterative linear with the inverse scattering series. You get, this is trying to do nonlinear AVO. That's a linear AVO. This guy here is trying to figure out, do you have an imaging problem or not? In other words, this is quadratic in the data. In other words, this is your data, and it does what it can do linearly. Yes? It just gives you that, which is a linear form, and will place them where water speed is. That's all it can do. Yes? This is quadratic in the data, because V1 is like the data. Quadratic in the data does what it can quadratically in the data. So one thing it does is it starts to give you nonlinear estimates of the changes in bulk modulus and density here. This guy is the guy dealing with leakage. That third guy. Yes? I mean, we learned to study that, you know. This one-parameter world only has a form like this. This looks like two-parameter, but suddenly there's another thing that talks crosstalk. It's a leakage corrector. You understand? There's a new issue in two parameters that doesn't exist in one. This guy, the underlined, is the imaging. The imaging. Why? Because in its world of amplitude, when you have an amplitude problem, it's local. In other words, at this point, I have something I'm trying to estimate. Yes? And I need to improve that amplitude. Imaging cares about how long have you had the wrong velocity. In other words, it figures out the duration in its own terms of the distance in the world that you have given it C0 where it should have been C1, let's say, yes? By an integral. Now, it doesn't have C1. What it does is this. If you give it C0, fine, it'll image this. If you give it two reflectors, yes, in a world, just say with only velocity, it knows that velocity is wrong. If the world is only velocity, and you give me two reflectors, a velocity changed here. Because that's in the world where only velocity changed, that's what must have happened. That means below, you got a different velocity, yes? What does it have? It has the timing of those two, yes? So from the timing of those two, it gets, and the reference speed, it gets an estimate. First, as soon as you get two reflectors, it knows it has a problem with one velocity, in a velocity-only world, understood? And they start to talk. The second one talks to the first to give it some help, okay? Here it's more complicated. Here you have velocity and density, yes? So what this inside here turns out, it determines from what's going on outside. If you add these two up, they have the same integrand. It turns out that this guy looks like the derivative of that. It's essentially the derivative of the data. And the data has possibilities. In other words, it's like a reflection coefficient. So it's like being imaged. And what this is, when this multiplies this, two things happen. They determine where there's an error in depth and a rough idea of how bad that problem is. You understand? So what this guy is doing in this two-parameter world, watch what it does. Let's say, in other words, this is a multiplication. Means you have data times data, nonlinear. So you allow events at one level to multiply and talk to another through that kind of machinery, yes? But watch what that integrand is, please. This is mind-boggling. I don't care how many times I see it. The integrand, please remember, the integrand is alpha 1 minus beta 1. You find alpha 1 minus beta 1 from that. Yes? You give me data at two angles, and I solve for alpha 1 and beta 1, because they don't depend on data, right? You give me data at theta 1, I write down theta 1, theta 2, and so on, right? And I solve two equations for alpha 1, beta 1. Understood? When you do that in those equations, and then you subtract alpha 1 minus beta 1, you get this formula. Alpha 1 minus beta 1 is the data of one angle minus the data at another angle over sine squared theta 1 minus sine squared theta 2. That just comes from looking at that first equation. Yes? It comes from this equation where I put in theta 1 and then theta 2, solve two equations and two unknowns, and then subtract alpha 1 minus beta 1, and you get this form, data of 1. So what is this about? Let's look at a reflection coefficient. This is, in other words, essentially a reflection coefficient as a function of angle. This is an exact expression for the reflection coefficient in acoustic medium, where it's C0 rho 0 and C1 rho 1. Yes? This is like Zollford's, but for the acoustic, it's simpler. Yes? Understood? So imagine that you had a reflector where it was rho 1, 0, rho 1, but this was C0 and C0. The velocity didn't change, yes? So if the velocity doesn't change, then that reflection coefficient, you'll get a 1 here, yes? You'll get a 1 here. If C1 is C0, yes? That will be a 1, and you get a factoring of the square root of 1 minus sine square from the numerator and denominator. Cancel. You see that? So if the velocity across here is the same, then R is independent of theta, yes? If R is independent of theta, R of theta 1 is R of theta 2, and alpha 1 minus beta 1 is 0. So as soon as Haiyan derived this form, yes, this came from the inverse scattering series. The integrand here said, you got to give me what alpha 1 minus beta 1 is. If alpha 1 minus beta 1 is not 0, you got a velocity change. If alpha 1 minus beta 1 is 0, it's a density only change. And it's excluded. It's not in the conversation between data and data. That reflects this out. That's interesting. Yes? That's a smart machine. Again, it's only because of one word, the direct word. Yes? As soon as you wrote the multi-parameter, it knew it had things to do. Now, the selection of terms here is going by only pick the terms that are dealing with structure. You understand? So with that selection, that is what, that kind of exclusion. So what we plan to do, and Shenzong Jiang will be working with Fang Lu, is we're going to look at the acoustic version of this, the elastic version of this, on realistic models where density change, which is Haiyan provided us the elastic version. Yes. The elastic version is more complicated. This is a piece of it. This is looking for changes in p-wave velocity. yes? And then there's a corresponding changes in shear velocity. Because if you have an image that's mislocated in an elastic world, it's possible that it had it could have been P, S, yes, to an image. It didn't have to be P and back. So the inverse scattering series is accommodating unknown P wave velocity and S wave velocity and density. And the imaging only terms, yes, look for changes in velocity of either variety. You understand? They assume that that can affect a structure. Clear? So we're going to be looking at, and there are extensions, there are tests. In other words, here's then work that was carried on once we had multi-parameter. Here we have density only changing, yes? No velocity change. Put it in the multi-parameter. The water speed image is this, and HOIS is the same. In other words, it doesn't get fooled. The water speed image is correct because the water speed is only density is changing here. Understood? It shouldn't move, yes, from the water speed image. Then all the other cases. In other words, there was a whole set of tests done. Here's constant density, okay, but the velocity changed. So then it does act. This is mislocated, yes, to the water speed because the velocity did change, and then it correct, yes. For example, on and on. Both change, okay, doesn't get confused. It's not a problem if both change, yes. Okay. And then polarity reversal, this was very important. Doug was saying, don't worry about parameters, changes in VP, VS, and rho. He said the worst kind of thing we suffer right now in AVO is when you have a zero crossing. They can't see that it's that type AVO. Because what happens with a zero crossing is when you get the data and they try to flatten it, yes, with the common image gather flat, so they get they change the velocity to try to make it flat. So they change it and it gets flat except for a bump. Then they change it again and that bump goes away, another bump comes, you know. And so they get sick of it and they take an iron and they just iron it with a filter. They said, now you're flat, you know. They just filter it. They get sick of this updating business. But in that filter, they can lose the zero crossing, is the problem, yes? That can damage that. And so he said, take a look where you have a zero crossing model. Here's a zero crossing. You can see it's positive and negative, mislocated. Can you preserve it at depth? Yes, at the right place. And then it's preserved, yes, through that process of imaging. They at least preserve the zero crossing. In other words, he said lower your ambition, okay, for you can reduce useful things. Anyway, this is a part of a delivery. There's going to be some evaluation this summer on the what conditions, working with Doug and Shanzong and Professor Fang Lu. We're going to look at under what conditions would this delivery be valuable where most of your reflectors, major reflectors, are not velocity, yes? And where their density is significant, we'll look at those acoustic and elastic variants, yes? And deliver some form of that. Understood? Again, some form of that means with incomplete capture, but fast, yes? As we build more capture, yes? Rather than just, what will this be someday? This ISS depth imaging, with sufficient capture will play the same role in your seismic imaging toolbox as your multiple method from the same form comes. It doesn't need a velocity and it doesn't have to propagate through it. Yes? It's just, yes, we just need more terms. Yes? but right now, we're gonna give limited capability and speed, and give it in stages as we build. Yes, that's the plan. Okay, so I think that's that talk. Now the next talk, in other words, we're moving from multiples to imaging to now kind of parameter estimation. How does inverse scattering series parameter estimation differ from iterative? Yes? That, yes, iterative updating. So, Chow, can you help me get the